Good morning, all. So we are in the third of our series of understanding capacitors. So first one, we learned what capacitance is, how it's defined, related to voltage and charge. Then we talked about the factors that affect capacitance, area, distance, and the dielectric between the parallel plates. Now we want to start thinking about putting capacitors in circuits. And before we put them in a circuit with resistors, which we'll come next, let's talk about when you have multiple capacitors in a circuit and how do they add, so to speak. So you can connect capacitors in series and parallel just like you can for resistors. So we're going to review the rules, the concepts behind it, and I'm going to do a few problems. So this might spill over in the second tutorial because there's a lot of little detail here. If you feel comfortable with resistors in series and parallel, this is similar with a twist. So let me remind you what we know about resistors, right? If we've got a series circuit with resistors, it's easy. We talk about the effective resistance is simply the sum of the individual resistors. And if we have parallel, all right, then the effective resistance is essentially 1 over the sum of, well, I'm not even sure if I'm writing that right. It's 1 divided by, sigma, right, 1 over Ri. Okay, so it's a reciprocal of the sum of the reciprocals. The equations for capacitance will have the same general form. It's just that, I'll tell you right now, series and parallel are flipped. So let's see why. So let's start with series circuits. It's capacitors in series. So on the diagram right here, I show 3 capacitors, could be different capacitance, in series with one another. And based on the diagram, what must be true of the comparative charge on each plate? Okay, so let's imagine this. We have charge coming out of the positive plate of that. This plate becomes positively charged, which induces a negative, same charge there. And it's got it labeled Q and negative Q. So by induction, it would make sense that if this plate is negative, it's going to make this plate positive. And it's got to make it positive by the same amount, regardless of what the capacitance is. That's just conservation of charge. And so whatever's induced on this top of the second plate is going to induce the opposite charge on the bottom of the second plate, which is going to induce the same amount of charge, so on and so forth. So regardless of capacitance, we see that the Q of the circuit is simply equal to the Q in each capacitor. They don't add together. They just, basically what you've got is essentially one big parallel plate between them all, broken into little chunks where each one has to have the same charge. Okay, so why must this be? That's really just conservation of charge. It would not make sense to have more charge on one plate than the other because there'd be an imbalance between that attraction and repulsion, and it would adjust itself. Now, how about the potential difference? So there's a potential difference across the circuit set up again by that voltage source. Like a resistors in parallel, resistors in series, we would get each one would have its own voltage jump such that they would add up to the whole. So our voltage of our source is equal to the V1 across each capacitor. And actually, why is this conservation of energy? I'm going to call Kirchhoff's loop rule, right? That's energy. And this is really just the junction rule. So note that in series circuits, the rules for resistors and capacitors are the same in terms of how charge must behave and how voltage drops must behave. However, the effective capacitance is not the sum of the individual capacitors like it is for resistors. And we can see why that is if we just combine those two rules with what we know about the definition of capacitance. So let's start with the voltage rule. So if I could say the voltage for my source is V1 plus V2 plus V3. Now we know from the definition of capacitance from C equals Q over V by definition, it would follow then that our voltage of the circuit is equivalent to Q of the circuit divided by the effective capacitance, right? I'm just taking this equation here and just writing it for the whole. Okay, now I do my substitutions, right? So V1 is going to be Q1 divided by C1 plus Q2 divided by C2 plus Q3 divided by C3. And if we go up to the junction rule for charge, right, we see that all the Q's are the same. So I can factor out this Q, and this Q, and cancel it out with this one, leaving a 1 for all these. I know this is getting messy. You don't have to write all this. But the upshot is then we get 1 over our effective capacitance equals 1 over C1 plus 1 over C2 plus 1 over C3. So the rules for charge and voltage again are the same, but the rule for effective capacitance is the opposite what we expect for a series. And so conceptually, more capacitors in series leads to less capacitance, and therefore less charge stored. And that's generally the goal of capacitors, is to hold charge, and if you want more charge, to get more energy. Okay, so you wouldn't necessarily expect that. So putting capacitors in series has its uses, but it's not to build up more and more charge. Okay, so let's look at a sample problem generically. So let's say I have well, I'm referring back to the diagram in the upper right-hand corner. We have C1 and C2 are the same capacitance. And we're going to say C3 is twice the capacitance. What is the effective capacitance of the circuit? Okay, so we would just say, I'm just going to solve for effective capacitance directly. That's 1 over C plus 1 over C plus 1 over 2C. If I work out the algebra, which I am confident you can do, we see the effective capacitance is 2/5 the original capacitor. So overall capacitance has dropped by putting them in series. How does the charge on 3 compare to 2? Right? So 3 has twice the capacitance as 2. You'd be tempted to say that it would have twice the charge, but that's not the case. They have to equal each other, again, by the junction rule, law of conservation of charge. How do the voltages compare? This is where we can now use the derivation I did, or at least for the thing. We know that voltage is proportional, not equal to 1 over C. So the voltage of 3 compared to the voltage of 1, that's what we're trying to find, is 1 over C3 divided by 1 over C1. So C3, so that's basically 1 over 2 divided by 1 over 1, which is 1/2. Okay? So voltage across 3 is 1/2 because it has twice the capacitance. And that's kind of like having the inverse of a resistor. If you're in series with a resistor, twice the resistance gives you twice the voltage drop. But with capacitance, because it's inversely related to voltage, you get the opposite result. Okay, so there's a little bit of digest there, but those equations are in your reference tables, at least the effective capacitance one, and you should be able to deduce the voltage and the current from the junction and loop rule. Now let's look in parallel. Okay, so I've got the schematic here of 3 generic capacitors in parallel, and by looking like that, it can kind of help you understand what's going to happen with the voltage and current or charge. It's the same idea. So the voltage, it makes sense, is going to be the same across each of them because they're in parallel. That's the hallmark of a parallel. If I've got a 12-volt drop here, I'm going to have 12 volts across here, 12 volts across here, 12 volts across there, regardless of the capacitance. It would also make sense, like current, that the charge is going to be distributed. Since this is its own little circuit, the amount of charge on here depends on voltage and capacitance. And then this one is going to be separate, and this one's going to be separate to give us a total. So they're going to have Q1 plus Q2 plus Q3. So now if I want to know what the effective capacitance is, I can start with this equation, right? And I'm just going to jump right into the substitution there. Oh, actually I won't. So actually I'm going to. So what is a Q in a circuit the same as? Well, again, if we use the relationship, I'm going to write up the side, that C is, by definition, Q over V, then Q is equal to CV. So I can put here the effective capacitance times the source voltage equals C1 times V1 plus C2 times V2 plus C3 times V3. And the V's are all the same. That's the loop rule, as we saw up above. So we're left with a fairly easy equation. The effective capacitance is the sum of the individuals. So capacitors in parallel add up, if you will, like resistors in series. So what's the upshot of this? More capacitance parallel lead to more capacitance. So I may have shown you that bank of capacitors that created the big spark in one of the tutorials. That's how you can do that. You take a bunch of little capacitors, you put them in parallel, you can build up a lot of charge. Right? Wait, therefore, I'm sorry, that should say more overall charge. Whoops. And therefore more overall stored energy. So generally that's why you'd use multiple capacitors, at least simplistically. So in doing a problem, now this is we have giving you individuals, we got 5, 6, and 9 nanofarads for how much energy is stored in the system if the voltage across it is 12. Okay, so we want energy, U. We have a few equations for energy. Since you're given capacitance, it makes sense that you'd want to express this energy in terms of capacitance rather than, let's say, charge. If I gave you a bunch of charges, then I would go with, we have two really equations that we use. We can say 1/2 QV is the common equation, but in terms of capacitance, that really becomes 1/2 CV squared. We did that derivation earlier in other tutorials. So I'm going to say this is the one that makes sense because we're given voltage and capacitance. So I can say the sum of the energy, all right, I'm not looking for individual energy, I'm looking for the whole, is simply going to be 1/2 of the effective capacitance times the voltage across the source. Okay, so what is the effective capacitance, right? Where CE is simply the sum of the individual capacitors. So if I put in the numbers 5, 6, and 9, okay, then I'm going to get 20 nanofarads. And then when I plug into the equation, I just got to make sure I got to take care of that nano. So that's going to be 20 times 10 to the negative 9th farads times 12 volts. And we get 1.44 times 10 to the negative 6 joules. Then we could ask what's the charge on each resistor, which would be like asking what's the current through each branch. Sorry, that shouldn't say resistor, that should say capacitor. I'll just call that a cap. Okay, and I'm not going to do the calculations. You can do that, but I'll set it up, right? So looking for Q, and I'm looking for individual, so I'll call that Q1. That's simply going to be the capacitance of the individual times the voltage. Q2 is C2V, and so on and so forth. Okay. Next one is a nice combination. So this is really test your understanding of all the parts and how it relates to the whole. And it's a really good exercise for you to go through. I'll walk you through it right now, though. Okay. In fact, well, here's what I suggest. I would pause this now and try to solve this problem. Okay. In fact, I think I've given the answers too. Look at me. I didn't even realize I did that. So wait a second. Yeah. Yep. Go ahead and solve these, and then I'm going to solve. You have the answers, but I'll put the solutions up in a second. All right, so here are the solutions to doing that. Hopefully you were able to get through most of it. Maybe I can see one mistake in particular that would arise. So in terms of effective capacitance, let me just make sure walk through this. This is in parallel to these two. So parallel, we add capacitance. So I'm going to add the capacitance of this to the combination of these two. So that's where this equation comes from. So C3 plus the combination. So this combination of the two in series is the 1 over equation. So I'm going to do 1 over C1 plus 1 over C2. So this C3 is 8. And if I do the math from here, I get 5/6. And then if I can make it a decimal, 8.83. Now, in terms of voltage across the circuit between here and here, that's simply the total charge in a circuit divided by the effective capacitance. In other words, that's why we found the effective capacitance. So the trick is, I gave you individual charges. I labeled them here in green. So the mistake that if you got this far, is if I've labeled 24, 3, and 3, is if you're tempted to say the overall charge in here is 30 microcoulombs. It is not. It's 24 here, and there's just 3 in this branch. Even though there's 3 individually, they don't add up to 6. So the charge in that branch is